Hi, and welcome to the next lecture unit in the lecture chapter on Gaussian processes, which is on common covariance functions for GPs. I'll give a couple of examples, including our good friend, the squared exponential, and the Matérn covariance function family. And then I'll explain the important property that the length scale parameters have on the shape of sampled functions from a Gaussian process. So let's remember this super important marginalization property of a GP, and that this implies that for any finite set of input values, input measurement points, the corresponding vector of function values is a Gaussian. So it's normally distributed like this here, usually with a mean 0 vector and a covariance matrix capital K. And this covariance matrix capital K is induced by the covariance function in such a way that we simply plug in all pairs of measurement points into our covariance function small k, and then compute the entries of this covariance matrix here. And technically, for every choice of inputs, capital K usually needs to be positive semi-definite in order for us to be considered a valid covariance matrix. And this is why we now introduce this property of the covariance function and say that a covariance function is called positive definite if every induced covariance matrix, doesn't matter where our points lie, and it also doesn't matter how many points we are considering, for every induced covariance matrix capital K, this matrix is positive semi-definite. The one thing that must hold for these points here is that they must all be different. Now, what was the purpose of such a covariance function? I mean, we wanted to use that, to induce the covariance matrix, but also to induce this spatial smoothness property into our Gaussian process. So if 2 points xi and xj are very close in x space, their function values should also be closely related in y space. And this close relationship of points in x space we want to measure through their distance. So this covariance function very, very often only depends here on this distance. And closeness in y space we wanted to express through correlation in y space of the outcomes. Let's visually explore this a little bit, although we might have already understood this before for the squared exponential covariance function for GP. I'm using a super simple one-dimensional input example here again using this squared exponential. I'm already writing it in terms of the distance, in terms of d, and yes, I could have also used here the absolute values instead of a norm. And I'm now considering two example points, x1 located at 3 and x2 located at 2.5. So these 2 points are reasonably close together here in input space. They have a distance of 0.5. And here on the left-hand side, I'm now plotting my covariance function small k, and I can now use that to immediately read off the correlation that the outcomes should have. So especially how correlated y2 should be in comparison to y1. So for this distance of 0.5, so what I'm kind of doing here is that I'm centering everything now around x1. So x2 has a distance of 0.5. So that results in me reading off the value here. And I can immediately see for such a distance of 0.5, there is approximately a correlation of 0.8 going on between the two outcomes. And that means if you have already observed a value y1 at x1, for example, minus 0.8, then there is only so much freedom now left for what we can expect that the outcome y2 should be. So that should probably be quite closely related. So in this case here, it's, for example, something like minus 0.4 So the function, we are not expecting our Gaussian process function to vary very much across this quite small interval here. So it should be quite smooth across this small interval. Now let's compare to yet another third point, which is not so close to x1. So x3, which is located here, I think a little bit to the right of x3 equals 5. And again, we compute the distance. That's a little bit more than -2. And we plug that in here again in the correlation function. And now we can see, because this correlation function goes down with exponential speed in relation to this to its distance argument, we can see that as at a distance beyond approximately 2, correlation between outcomes has nearly vanished. Yeah? So it's nearly 0, which means we can basically expect anything here, being the outcome at y3, although we already know what happens at y1. Let's introduce now a couple of commonly used properties and types of covariance functions. So abstract properties, so we will call K stationary if it can be written as a function of only a distance vector d. And then we simply write K of d. I already did that on some of the slides before. And stationarity means invariance to translations in input space. So I can shift both of my arguments here for the same amount. So for example, I can shift for the amount of x. And this doesn't change the correlation value. And that kind of implies that this is not a 2-argument function anymore. It's kind of just a 1-argument function anymore. Just a 1-argument function, which only depends on this d thing here. I can take this even a step further, and I can call a function now isotropic if it is a function of only the length of that distance between x and x dash. So then I can write it as a kernel function or covariance kernel with respect to r, where r is that length of the distance. And isotropy is invariance also to rotations of the input space, and it obviously also implies stationarity. And I will call a kernel function a dot product function if it is a function of x transposed x dash. Here are a couple of commonly used examples of covariance function. So there's, for example, the quite boring constant covariance function. There's the linear covariance function, which is a dot product covariance function. There's the polynomial, which is also a dot product covariance function. Here's our squared exponential that we have seen before, and we'll see this again on the next couple of slides. And there's also the more complicated Matérn covariance function that also depends on this length scale parameter here, which has basically the same effect as the length scale in the squared exponential, and which I will discuss on the next couple of slides. And this also has this new parameter here that controls the differentiability of the associated Gaussian process. Usually we can kind of see the Matérn family as a maybe more realistic family of functions for physical processes, because we can kind of control through that parameter here that the resulting process is not too often differentiable, which is often true for more realistic processes in the real world. And then there's also this exponential covariance function without the squaring. To get a feeling for some of these examples, I've visualized them here. So I've visualized our good old friend, the squared exponential covariance, with a couple of different length scale parameters, as you can see again here. Well, not again, but maybe for the first time. But I'll discuss this a lot more on the next slides too, is how the length scale influences the wiggliness and the smoothness of our sampled functions. So small length scale implies quite a wiggly function. Large length scales imply smoothness, less wiggliness. Here are polynomial covariance functions with different degrees and sampled functions from these. And here you can see the Matérn covariance function. Here I haven't varied the length scale. That would have a very similar effect as for the squared exponential. Here I've varied this new parameter, and you can see, hopefully you can kind of see what I mean with this differentiability that is affected through the new parameter. So the larger nu becomes, the more kind of differentiable the process becomes. So at least you can hopefully see this visually from the roughness here of the resulting curve. So I don't want to go into too much detail here now. What I do want to study more is how this length scale parameter actually influences things and how we can generalize this also to multiple length scales. So again, here's the formula for our squared exponential. We can hopefully now easily see that this formula here only depends on the length of the distance between x and x dash. So we can also write it in terms of r, and we can call this function isotropic and therefore, of course, also stationary. This covariance function and the associated GP are what we call infinitely differentiable. This implies a certain extreme smoothness of all of the associated sample paths of such a Gaussian process. And like I said, this is sometimes deemed unrealistic for modeling of many physical processes. If your scenario falls under such a category, maybe rather move over to such a Matérn covariance function that I've visualized here. I think we have seen this before, how this characteristic length scale affects the shape of functions. So loosely speaking, the characteristic length scale describes how far we need to move in input space, so how large we have to make an interval between measurement points so that function values become nearly uncorrelated. So higher L induces smoother functions, lower L induces more wiggly functions. So this lower L allows us to model much more locally than if we would use something like this here, which means that the function can only very slowly vary across smaller intervals. And as I've said now a couple of times, the really nice thing about Gaussian processes is that we don't have to pre-specify these hyperparameters, or that we also don't have to do super expensive extra external tuning. We can learn these hyperparameters directly in the training of the GP. Until now, I have mainly shown one-dimensional input domains and used one-dimensional examples. That's, well, maybe good for teaching purposes to keep it simple. But from a machine learning modeling perspective, of course, rather boring. Most of our data situations will have multi-p-dimensional input spaces. And for these cases, it very often makes sense to generalize this squared exponential to a form where we are using not one length scale hyperparameter, but p length scale hyperparameters. And we can get away with being able to use p and not only one hyperparameter because, like I said, we can later on see how we can directly learn these hyperparameters in the GP. So we can now generalize this formula here for the squared exponential to a form that looks like this, where we have our distance vector d transposed times a matrix M times the distance vector again. And very often we write this matrix M in through one of these following three forms. We can use the identity matrix just divided by L squared. And then we're basically in this case, and I'll visualize these three cases also very soon. So this kind of implies that we now we have one length scale parameter at our disposal, and that influences the wiggliness of the function over all input dimensions in the same manner. So less flexible, less control. If we compare this for example, to this second case here, where M becomes a diagonal matrix, and on this diagonal we have L1 squared, L2 squared, L3 squared, and so on until LP squared. In this second case, you can also write down in a much more, I guess, simpler and more readable form, where here in the exponential function you have minus a half times the sum, where you go over all of your features and then you do dj squared divided by lj squared. So you have these lengths. I guess now also this name length scale really makes sense here, because you're scaling here these distances for canonical input directions, direct input feature directions. And there's a third form, which is a bit more complex, where we are assuming that we are decomposing here our matrix M3 into two parts. So like, I don't know, like you might have seen as an eigenspectrum decomposition, eigenvector decomposition, where you have like certain important directions going on here, which don't have to be along these canonical input directions, and then you can scale these directions with these L length scale hyperparameters. I guess it makes sense to visualize this now. Well, okay, maybe before we do that, a couple of general comments. So yeah, okay, these L1 to LP, we call them characteristic length scales. I've explained that. They describe how far we now need to move along an axis I, or a certain axis I, either an input space or along another predefined, more complicated direction, for function values to become uncorrelated, as before in the simple case where we only had one L. And such covariance functions, especially this second guy here, this guy, this is what we often call automatic relevancy detection, or the automatic relevancy detection kernel, since the inverse of the length scale Li determines the relevancy of the input feature I to the regression. If Li is very large, the covariance will become almost independent of that input. So if that guy is quite large, this Lj, and then we square it, will become even larger, then this distance here in the jth direction will be pushed down nearly towards zero. So this will not make any difference anymore in the computation of the correlation. And therefore the feature will be kind of nearly switched off and effectively removed from the inference process. And also what's quite nice, if our features are on completely different scales, we can kind of rescale automatically our data by estimating these L's. Okay, now it's really time for a visualization of this complicated beast. So I've visualized here exactly these three cases from before. So in this first case here, we have our M matrix as the identity matrix with just one length scale parameter. And I do have now this length scale parameter at my disposal, and I can change the wiggliness and the speed of the varying of the function. But I can only do this like on a global level for all input dimensions at the same time. And you can also see here that my function now kind of varies the same in both directions, x1 and x2. And in this second case here, I have used this automatic relevancy detection kernel with, on the diagonal of my matrix, I have now two hyperparameters L1 and L2, where L1 is smaller than L2. And the function now varies less rapidly as a function of x2. I can see this here. If you follow visually along this x2 direction, not much exciting stuff goes on here, but it varies quite a lot more if you follow this x1 direction. And this is because of these two different values here, and you can control this by setting these, or later on, hopefully by learning these in a data-dependent manner. And this is the most complicated case where through this decomposition here, you can now specify certain directions where you want, like non-standard directions, where you want to control this variation through your length scale parameters on these non-standard rotated axes.